And record. All right, so today we are going to start on section 4.1, which covers related rates. Okay, so this section basically gets all the stuff we've learned so far and puts it into application. Okay, so just to kind of give you an idea of what we'll be covering in this section. So let's say if we know that the volume of a cone is equal to pi over 3 times the radius squared times the height. Okay, so let's say if we have a cone and it's filled with some liquid all the way to the top. Okay, well, we know that the radius is the center of the base just above or below the apex, and the distance to the outer edge, that's your radius. And we know the height is just how high up in the cone that it's going, that the liquid is filled to. Okay, so what if someone decides to get a needle or a knife and poke a hole in this cone? And we can see that little by little, the liquid is dripping out. Well, if that liquid is slowly dripping out, either slowly or quickly, either way, then we know that after a while, that liquid is only going to maybe come up to here. Where your radius is now a little bit smaller and your height is a little bit smaller. And remember, that liquid is still just dripping out. Okay. So again, after a while, it's just going to keep dripping out until it's almost empty. Where your radius is even smaller and your height is even smaller. Okay, so as the height and the volume get smaller, I mean the height and the radius get smaller, the volume will also get smaller. So we know that the volume of a liquid is related to the radius and the height. To make that capitalized. So the volume of the liquid in the cone is related to the height and the radius. The more you fill up the cone, the higher the volume. The more liquid leaks out, to lower the volume. Okay. So what if we wanted to figure out a formula to find out the rate of change of the volume with respect to either the radius or the height? Or we can make it with respect to time. Okay, so if we want to find rate of change with respect to t of the volume, that's just equal to pi over 3 times the derivative with respect to time of the radius squared and the height. Okay, so we know here we have two terms or two factors being multiplied that we're trying to find the derivative, so we know we're going to have to use the product rule. Okay, so the rate of change of the volume with respect to time is equal to pi over 3. And if we get the product rule, we have the first function times the derivative of the second. So we have r squared times the derivative of h with respect to t, plus the second function times the derivative of the first. Okay, and remember, derivative with respect to time of r squared. I'll write that first and then do the steps. Okay, so that means the rate of change of the volume with respect to time is equal to pi over 3 times r squared times the rate of change of the height with respect to time, plus the height times the rate of change of the radius with respect to time. And again, whenever you have a different independent variable, we know we have to use the chain rule. So we take the derivative, and again, sometimes if you want, you can put the r in parentheses. Let's say r squared. Same thing, but sometimes the notation helps. Okay, so if we take that derivative, we bring down the 2 times r to the power of 2 minus 1 times the derivative of what's inside. So the derivative of the radius with respect to time. Okay, so the rate of change of the volume with respect to time is equal to pi over 3 times r squared times the rate of change of the height with respect to time, plus 2 times r times h times the rate of change of the radius with respect to time. So now with this formula, we can find out how fast is the volume increasing or decreasing, which will pretty much tell us just how fast is that liquid leaking out. Is it leaking out more when it's full? As it gets lower, does it leak out a little bit less? Now, you don't have to memorize this formula or anything like, oh, forgot my closing bracket or anything like that. As long as you know how to calculate it, you're fine, because it's way too many of them to try and memorize. Yes. Oh, sure. All right. Okay. Anyone still writing? All right. Okay. So let's say, for example, suppose that x and y are both differentiable functions, which means the derivative exists. Of t. Uh-oh. Don't know what period there. And they are related by the equation y equals x squared plus 3. And we want to find the derivative of y with respect to t when x is equal to 1, and it's given that your dx dt is equal to 2. Okay. So a lot of times when you see an x equal 1, your first instinct is to plug it in. You don't want to do that here. Only because if you plug in 1, then that just gives you the position of y. Because remember, that's just your position function. We want to find the rate of change of y when x is equal to 1. So we don't want to plug in x is equal to 1 just yet. Even though every thought in your head is probably saying just plug in the 1. Because that's what we've been doing so far. Just whenever we want to find f of 1, we just plug in 1. But here it's just a little bit different. Okay, so let's look at everything that was given to us in this problem. Well, we know that x is equal to 1. And we know that dx dt is equal to 2. And we know we want to find dy dt. Or you could say you want to find dy dt when x is equal to 1 and dx dt is equal to 2. Okay, so we start off with our y is equal to x squared plus 3. Okay, so we're looking for dy dt, so we know our independent variable is t. So the derivative with respect to t of y is equal to the derivative with respect to t of x squared plus the derivative with respect to t of 3. Okay. So with the last term, it doesn't matter what the independent variable is, the derivative of a constant is always going to be 0. So we know that disappears. This derivative with respect to t of y, because it's just y by itself, you can just write it as dy dt. Is equal to the derivative of x squared. Now, if this was just x, we just write it as dx dt. But because we have the x squared, we have to use the chain rule. Okay, so we know that the derivative of x squared with respect to t, considering these two independent variables are not the same, we do the power rule on the x. So we have 2x times the derivative of x. Okay, so then this derivative gave us all of that. And this is 0. You don't have to put plus 0, but I'll do it anyway. Okay, so now our dy dt is equal to 2 times x times your dx dt. Okay, so now is when we use our x and dx dt. So when x is equal to 1 and your dx dt is equal to 2, we know that our dy dt is equal to 2 times x. So that's 2 times 1 times dx dt, which is 2. So we know that our dy dt is equal to 4, or rate of change of y with respect to t. All right, so any questions on that one so far? Yes.
Did they cancel to 0 because there's no x, right?
Yep, exactly. Whenever you have just a constant, the derivative of a constant is always going to be 0. Okay. Now with this one, they gave us our primary equation, where we're going to start with. But in some problems, they don't tell you the primary equation. They just kind of give you hints as to what the primary equation should be. All right, anyone still writing? All right. So let's say, for example, if you know that air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. And if you wanted to, you could rewrite 4.5 as 9 divided by 2. You don't have to, but sometimes if you're looking for an exact answer, you just convert it to fraction form. Okay, so what if we want to find the rate of change of the radius when the radius is 2 feet? So again, they didn't give us a primary equation, but look at the fact that it's a spherical balloon. Then we know that we're looking for the volume of a sphere. We know that the volume of a sphere is equal to 4 over 3 times pi times the radius cubed. Okay, so let's look at what's given. What information did they provide? Okay. So we know the rate of change of the volume with respect to time, because it's being pumped in at a rate of 4.5 cubic feet per minute. That's the rate that the volume is changing. So 4.5 cubic feet per minute. And again, if you like, you can rewrite it. Again, you don't have to, depending on the form that they want the answer. Okay. And we know that we want to find the rate of change of the radius with respect to time. When the radius is equal to 2. How fast is the radius increasing or decreasing right at that point when it's actually equal to 2? Okay. So again, we start with our primary equation. Volume is equal to 4 over 3 times pi times the rate, make that a little bit closer, times the radius cubed. Now we differentiate both sides with respect to the independent variable, which in this case is t. So the rate of change of the volume with respect to time is equal to, and we can go ahead and factor out those constants. So we could say 4 pi over 3 times the derivative with respect to time of the radius cubed. Which means the rate of change of the volume with respect to time is equal to 4 pi over 3. And again, we see we have two different independent variables, so we know we're going to apply the chain rule. So this derivative is 3r. So we just brought down the 3. Now we subtract 1. So 3r squared times the derivative of what's inside, which is r. So the derivative of r with respect to t. Excuse me. Okay. Well, we can see here that the 3's will automatically cancel each other out. So we can do that now. It wouldn't affect the answer at the end, but might as well make it as simplified as possible. So the rate of change of the volume with respect to time is equal to 4 pi times r squared times dr dt. Okay. Now for this problem, we're actually solving for our dr dt, so we have to isolate it. So we want to divide both sides by 4 pi r squared. So this is actually our rate of change of the radius with respect to time t. So that's why I always sound out the whole thing. The rate of change of the volume with respect to time. Instead of just saying dv dt, kind of helps reinforce what dv dt actually means. Okay, so if we divide both sides by 4 pi r squared, of course, everything there cancels out. Divide this side by 4 pi r squared. And we know the rate of change of the radius with respect to time, or your dr dt, is equal to the rate of change of the volume with respect to time divided by 4 pi r squared. Okay, well, they gave us the rate of change of the volume right at the very beginning. And we want to know when the radius is equal to 2. So if they were looking for the exact answer, we just use 9 divided by 2 instead of the 4.5. Divided by 4 times pi times the radius squared, which is 2 squared. So we can get the numerator and just bring it down to the front and just say this is 9 divided by 2 times 4 times pi times 4, 1 over 16. Oh, no, 1 over 16 pi. So if they did ask for the exact answer, it would be 9 divided by 32 pi feet per minute. This is your exact. Okay, so when they say exact, they just mean no decimals, leave pi as pi. But if you plug that into your calculator, you'll get 0.0895 approximately feet per minute. And that's just your decimal approximation. So again, normally they'll say it at the beginning, write your answer to the nearest 4 decimal points, or leave the exact answer, or write your answer in terms of pi, which would be this one. So they'll usually tell you how they want the answer. Very rarely they'll slip up and leave that blank. All right, any questions on that one? All right, anyone still writing? All right. So let's say, for example, we know that a square has a side length that is increasing at a rate of 19 inches per minute. And we want to know what is the rate of change of the area when the side length is 5 inches. Okay. So again, they did not give us a primary equation to work with, but they gave us everything we needed to figure out what the primary equation is. First, we know that we're dealing with a square. And even though they said the square has a side length that is increasing, the one thing about a square is that all the sides are the exact same size. So if this is a length of, let's say we'll call that S, and I'll put a line through it in case I'm writing fast so it doesn't look like a 5. And we know it has a width of S. All sides are the same length. So if we're looking for the rate of change of the area, that means we have to start off with the area of a square. So the area of a square is equal to the length times the width. Or in this case, the length and the width are both S. So the area is just equal to the length of the sides squared. That's your length times your width. Okay, so let's look at what was given to us. Okay. So we know the side lengths are increasing at a rate of 19 inches per minute. So if the lengths are increasing at a rate of 19 inches per minute, that means the area is growing at a rate of 19 inches per minute. Okay, but with this one, we're just looking at the side length. So we know that the rate of change of the side with respect to time is 19 inches per minute. Okay, so this side is increasing at 19 inches per minute. This side is increasing at 19 inches per minute. So both are increasing at 19 inches per minute. We want to see how fast is the whole thing increasing as far as the area. Okay, so we know that we want to find the rate of change of the area with respect to time. They kind of told us what we're going to find, or what they want us to find. When the side length, which we'll call S, equals 5 inches. Okay, so just like always, we start with our primary equation. The area of a square is equal to the side length squared. So if we take the derivative with respect to time on both sides, that gives us the rate of change with respect to time of the area is equal to the rate of change with respect to time of the sides squared. Okay. Well, since this is just a variable a, we could just rewrite this as the rate of change of the area with respect to time. And that's equal to, okay, this is s squared. So because these two are different independent variables, we have to apply the chain rule. I'm going to go ahead and put that in parentheses. There we go. So we apply the power rule to the whole thing. So that's 2 times s to the power of 2 minus 1, which is just 1, but I'll write it out anyway, times the derivative of what's inside, which is the derivative of s with respect to t. So we know the rate of change of the area with respect to time is equal to 2 times s times the rate of change of the side length with respect to time. Okay, so now we can take everything here and plug in the values that we were given. Which means that the rate of change of the area with respect to time is equal to 2 times s, which is 5 inches, times the rate of change of the side with respect to time, which is 19 inches per minute. So the rate of change of the area with respect to time is equal to 19 times 10, which is 190. So we have 190 squared inches per minute. All right. So any questions on that one? All right. Anyone still writing? Okay. There we go. So let's say for this one, you know that a box has a width of 12 centimeters and a length of 9 centimeters. Okay, so we know that the volume of the box is decreasing at a rate of 541 cubic centimeters per second. With the width and length being held constant. Uh-oh, I don't know why I put a D there. And make that a little neater. There we go. Okay, so we want to know what is the rate of change of the height. In centimeters per second, when the height is 6 centimeters. Okay, so again, they don't tell us our initial or primary equation, but we know that we're dealing with a box, and they also measure the volume of the box that is decreasing in this case. So we know we're looking for the volume of a box or a cube. Well, it wouldn't be a cube because a cube have all the same length. So it's just a volume of, I don't want to say rectangular prism, that's a little too, I'll just say the volume of a box, even though it's considered a rectangular prism. I just seemed like an unnecessary term to use here. Okay, so we know that's equal to the length times the width times the height. Or you could just say the volume is the length times the width times height. Okay, now this list of givens are a little bit tricky. Okay, so we know that the width is 12 centimeters. And your length is 9 centimeters. Okay. Thing is, both are held constant. Which just means that if you have your box, the length and the width are staying the same, it's just getting shorter. The height is shrinking. So that means your rate of change for the width and the length are 0 because they're not changing at all. So that means rate of change of the width with respect to time is equal to 0, because remember the derivative of a constant is just 0. And the rate of change of the length with respect to time is equal to 0 because it's not changing. Clean that up a little bit. There we go. So we know we're not even going to need those. Plus, when you see that the volume is decreasing, and I'll put it underneath it. Just looks like I'm going to run out of room. That just means the rate of change of the volume with respect to time is just negative 541 cubic centimeters. So all the examples we had before, when it was increasing, it was always positive. But whenever your rate of change is decreasing, it's going to be negative. So that means we want to find the rate of change of the height with respect to time when the height is equal to 6 centimeters. Okay, so if you have a box and you know the length and the width are remaining the same, it's just getting shorter and shorter and shorter. At exactly 6 centimeters, how fast is it shrinking at that point? Okay, so we're going to apply our derivative with respect to t on both sides. But with this one, you have to remember your length and your width are constant. Which means we treat those as constants, or you could even plug in your 9 and 12 here, because it doesn't change. So that means the rate of change with respect to time of the volume is equal to, since these are held constant, we could just factor those out like we could any constant. So it's the length times the width times the rate of change with respect to t of the height. Which means if we have the rate of change of the volume with respect to time, that's going to equal the length times the width times the rate of change of the height with respect to time. Okay. So since we're looking for the rate of change of the height with respect to time, we have to get rid of that length times width, which means we just divide both sides by that length times width. For those two cancel each other out. So we know the rate of change of the height with respect to time is equal to the rate of change of the volume with respect to time divided by the length times width. So I'll just switch those around. Rate of change of the height with respect to time. We'll make that a little higher up. rate of change of the volume with respect to time divided by the length times width. So we already know our rate of change of the volume is negative 541. And we know our length and width are 9 and 12. So our length is 9 and 12. Okay, so you can just rewrite that as negative 541 over 108 if they want the exact answer. If they want a decimal approximation, then you just plug that into your calculator. Oops. Centimeters per second. All right, so any questions on that one? All right. Okay, looks like everyone's done writing. So let's say, for example, if we have a triangle that has a base that is decreasing at a rate of 19 millimeters per minute, and a height that is constant. So we want to know what is the rate of change of the area of the triangle and the height is 4 millimeters. Okay. So with this one, they kind of gave you a bigger hint when they said find the rate of change of the area of the triangle. That's a way of pretty much telling you what the initial equation should be, the area of a triangle, which is equal to 1/2 times the base times the height. Okay, so let's say that for a moment you forget that the height is constant. Okay, so let's just say that our given, we know that the base is decreasing at a rate of 19 millimeters per minute. So the rate of change of the base with respect to time is equal to negative 19 millimeters per minute. Okay, so let's say if we go ahead and apply the derivative with respect to time to both sides. So we know the rate of change of the triangle is just when we apply the rate of change with respect to time of the area is equal to 1/2 times the rate of change with respect to time of the base times height. I should put of the area of a triangle to be a little more specific. Okay. Now, since h is constant, we could just factor it out with it. But again, let's just pretend that you forgot that it's constant. You go all the way through. So the rate of change of the area with respect to time is equal to 1/2. But we see here we have the product of two variables. So we have to use the product rule. So we have the first function, which is b, times the derivative of the second, plus the second function times the derivative of the first. Okay, so let's look at the fact that we know that h is constant. Okay, so we know that h is equal to 4 millimeters. So now the derivative of h with respect to t is equal to the derivative with respect to t of 4. Which means your dh dt is equal to 0. The derivative of a constant is always 0. Or the rate of change in this case is 0. Okay. Which could happen because I've had students actually work this out and then say, okay, they didn't give us the dH/dt, and couldn't figure out why. So whenever your h is constant, we already know that's going to be 0. So 0 times whatever this is doesn't matter. That's going to be 0. So if they don't give you something, there's probably the reason is probably you don't need it. So even if you work it out and you say, okay, why didn't they give us that? That would probably be the reason, especially when you're dealing with constants. So you want to be careful with that one. Okay. But again, if we remembered and factored out the h, it would just be 1/2 times h times dB dt, which is what we're going to end up with here. Equals 1/2 times h times the rate of change of the base with respect to time. So either way, we end up with the same thing. It's just a matter of how long it took us to get there, which in this case wasn't bad, just a couple of extra seconds. Okay, so again, we know the rate of change of the base is negative 19 millimeters per minute. So the rate of change of the area with respect to time is equal to 1/2 times the height, which we already know is equal to 4. So 1/2 times 4 times negative 19. Okay, so we know the rate of change of the area with respect to time is equal to negative 19 times 4 divided by 2 is 2. So that will give us negative 38 millimeters per minute. So every time you remember going back and you saw derivative of a constant is 0, derivative of a constant is 0, this is where it kind of comes in handy. Yes?
Wouldn't the units be millimeters squared a minute because height is also millimeters?
Oh, yep, it is. Thank you. Yep, millimeters squared. And normally I remember to put that next to it just to remind me of that. That should be millimeters and negative 19 millimeters per minute. And millimeter squared. Thank you. All right. Any other questions on that one? All right. Now, some of them are pretty straightforward, and some of them can get a little bit lengthy depending on what they're asking for and what they want you to, what information they give you. So let's say, for example, we have a street light. Let me write out the actual street light instead of just light. Is at the top of a pole that has a height of 11 feet. Okay, so if we have a woman that is 5 feet tall, walks away from the pole, at a speed of 2 feet per second along a straight path. So we want to know how fast is the tip of her shadow. Moving away from the pole. When she is 15 feet away from the base. Of the pole. Okay. Now this one can get a little bit tricky only because you have a lot of moving parts in this problem. So just to help visualize anything like this, it just helps to make a quick sketch so you can see exactly what you're dealing with. Okay, so let's say if we know we have an 11-foot pole, with your light on top, and we know that's 11 feet. Clean up that parenthesis a little bit. Okay, so she's walking along a straight path. So let's just say this is the ground. And here she is at 5 feet. And make that a little lower. Go. Walking away from the pole. So let's say the tip of her shadow is right here. Light is shining, tip of her shadow is right there. Oops, there we go. And let me see if I have any index cards I can use. That's a little too big. I'll use that. So if we draw a line from the light to the tip of her shadow, and I'll put it like that. You can see there that we have a right triangle. Okay, so let's say this is our distance from the pole to the tip of her shadow. So we'll let y equal that distance. Okay, we have no idea what it is, but that's the distance. Okay, so let's say if we let this distance, I'll just draw another arrow. We'll let x equal the distance from the pole to where she is. Which means the length of her shadow, we look from here to here, and I'll draw it underneath it. That's the entire distance minus the distance from her, between her and the pole. So this entire distance is just y minus x. So that whole thing minus that part. So if we redraw this without all the people and everything else, what we have is a right triangle with a vertical 5-foot line. We know that this line has a distance of x. This has a distance of y minus x. Where the pole is with a distance of 11. And we know that since she's walking away from the pole at a rate of 2 feet per second, that means this distance, this x, is changing at a rate of 2 feet per second. So the rate of change of x, or the rate of change of her distance from the pole with respect to time, is equal to 2 feet per second. Okay, what is that? All right. Now, just from the last sentence, we know we need to find that the rate that the tip of her shadow is moving away from the pole. So we need to find the rate of change of the distance between the tip of her shadow and the pole. I'll make this a little bit bigger. Okay, so in other words, we need to find the rate of change of that distance with respect to time when that distance away from the pole is equal to 15. Oop, there we go. All right, anyone still writing? All right. Okay, let me just redraw the triangle really quick just to give us an image so we don't have to keep flipping back and forth. X, y minus x. Rate of change of x with respect to time is equal to 2. And the distance of the entire thing is y. Okay. Now that triangle is actually a really big help. The only problem is you have to go back and use the method of similar triangles, which if it's been a while, you might have forgotten because it's not something you use a lot outside of math. Okay, so what we do is we just kind of ignore, well, that's a little bit big there. We just kind of ignore this middle line here. Okay, so we look at the entire triangle minus that vertical line there. So if we take that entire triangle, you know, this is a length of 11, and this whole length is y. Now we look at just the smaller triangle. So if we compare that to the smaller triangle, you know, the height of this one is 5, and this one is y minus x. Okay, so these two triangles have a similar shape, which means that they're proportionate to each other. Which means you can write it as a proportion, where the left side is proportionate as a ratio of the other left side, and the bottom of the triangle is proportionate to the bottom of the other triangle. So we have the ratio that 11 is to 5 as y is to y minus x. So with a question like this, you have to kind of remember your ratios and proportions. They help. Okay, so we know that we can solve this by just cross multiplying. Okay, so we have 5 times y is equal to 11 times y minus x. And make that equal sign a little clearer. There we go. So if we distribute that 11, that gives us 5y is equal to 11 times y minus 11 times x. Okay. Now, since we're looking for the rate of change of y, we have to find a y equation to use. That's why we had to go through all of this. So we want to isolate our y. So we subtract 11y from both sides. These two cancel each other out. So we have 5y minus 11y, which is negative 6y, is equal to negative 11x. So if we divide both sides by negative 6, where those two cancel each other out, we have y is equal to, negative divided by negative is positive. So that's 11 over 6x. So it took a little while, but we finally have our primary equation. Okay, so now we can differentiate both sides and find our rate of change of y with respect to t. So we have the derivative with respect to t of y is equal to that 11 over 6. We can go ahead and factor that out, times the derivative with respect to t of x. Okay, so again, this is just y by itself, so we can just rewrite that as dy dt is equal to 11 over 6. And this is just x by itself, so we can just rewrite that as dx dt. Okay, so if you remember, where did I? Dx dt, I did put it up there, forgot about that, is equal to 2. And we want to know when x is equal to 15. Which is what we kind of isolated over there on the first page. Okay, so the rate of change of the distance of her shadow, the tip of her shadow, with respect to time is equal to 11 over 6 times the rate of change of the distance between her and the pole with respect to time, which is 2. Feet per second. So that gives us 22 divided by 6 feet per second. Or you can simplify that to 11 divided by 3. We'll do that. Just put it in its simplest form. And again, this is just the exact version of it. So they might say, leave your answer as a fraction or an exact form. Then you'll leave it like that. Or plug that into your calculator. It's approximately 3.67 feet per second. Let's see. Yep. All right. Any questions on that one? All right. So now we are going to start on section 4.2. Oops. And that covers linear approximation, and differentials. Okay, so if you remember, we've had a lot of uses for the point slope formula. Y minus y1 is equal to the slope times x minus x1. Okay, so let's assume that the function is differentiable at some value x equals c. Is differentiable at x is equal to c. That means your point on the graph would be x f of x or c f of c. Well, since we're looking for the point, we'll say that's our point x1, and that's our y1. And we know that the slope of the tangent line that's just your derivative at that point C. So if we rewrite this, instead of y minus y1, we could say y minus f of c, since that's our y1. Is equal to your slope of the tangent line, which is f prime of c, times x minus x1, or x minus c. So what if we add f of c to both sides? And that gives us y is equal to f of c plus f prime of c times x minus c. And just to kind of give this formula its own identity, let's say we'll call it L of x is equal to f of c plus f prime of c times x minus c. So this formula right here gives us our linear approximation. Or they also call it the tangent line approximation. Move that up just a little bit. Okay, so what if we have, just to kind of leave it in this form, and if we subtract f of c, we leave it back in this form. So y minus f of c is equal to, we've got to close off that one. There we go. F prime of c times x minus c. Okay, so just to kind of help visualize, we have some function. Let's say this is your value x, which means this is your f of x. And if this is some value c, which means this is your f of c. make these a little consistent, I'll draw a line for this one too. There we go. Okay, so now your distance between f of c and f of x, this is just your change in y. And your change in y, that is denoted as delta y or your dy. So this we'll just change to dy is equal to, and now you have your x and your c, which gives us our change in x. Which is denoted as delta x or dx. So that gives us our dx. Okay, so it's f prime of c, well, dy is equal to f prime of c dx. This is your differential form at x is equal to c. But honestly, the easier way to find the differential, instead of going through all that, just remember that derivative of y with respect to x is equal to f prime of x. So if you multiply both sides by dx, that just gives you dy is equal to f prime of x dx, which is a lot easier way to access it. This one's more of just an explanation to end up with the exact same thing. And then you plug in your value of c. All right. So let's say, for example, you want to find your dy of the function y is equal to 4x to the fourth power plus 5x to the third power plus 2x squared. Okay. So again, all you have to do is just remember that your derivative of y with respect to x equals f prime of x. And our dy is just f prime of x dx. Okay. So we just have to find our derivative. So the derivative of y with respect to x is equal to 4 times the derivative of x to the fourth power. So we use the power rule, bring down the 4, times x to the power of 4 minus 1, which is 3. Plus 5 times the derivative of x to the third power, bring down the 3, times x to the power of 3 minus 1, which is squared, plus 2 times the derivative of x squared, bring down the 2, times x to the power of 2 minus 1, which is just 1. So we can leave that there. So we know our dy dx is equal to 16x to the third power plus 15x squared plus 4x. It means your dy is just equal to this entire derivative, 16x to the third power plus 15x squared plus 4x with respect to x. So really all you have to do is find the derivative, and you can put it in differential form with no muss and no fuss. A little bit. So let's say if we wanted to find the differential of y is equal to the square root of 6 minus 2x. Excuse me. Okay, so again, all we have to do is start off with our dy dx, but first we have to rewrite this square root. So it's 6 minus 2x to the 1/2 power. So now we can apply the power rule. So the derivative with respect to x of y is just using the power rule, bring down the 1/2 of 6 minus 2x to the 1/2 minus 1 power, which is negative 1/2, times the derivative of what's inside. So the derivative of 6 minus 2x is just negative 2. So we know that our dy dx, and actually we can simplify it because this 2 and this 2 cancel each other out. That's equal to 6 minus 2x to the negative 1/2 power. We can move it to the denominator to make the exponent positive. So that's 1 over the square root of 6 minus 2x. Nope, forgot the negative, because that negative did not cancel out. Okay, but if we want to write it in differential form, it's just dy is equal to negative 1 over the square root of 6 minus 2x dx. Okay, any questions on that one? All right. So let's say, for example, if we wanted to find your delta y and dy for y is equal to sine of 2x. Okay. So remember, your delta y, that's just your change in y. Which you can write it as f of b minus f of a, or f of x plus h minus f of x. The only reason I'm doing that one is because this is a function of x. Okay, so if we had, let me move that a little further over, make sure I have enough room. Okay, so we know that our y is equal to sine 2x. Which means that your delta y is equal to 2, oh, actually 2 times sine of 2x. Where did I, oh, forgot my 2. That's why I was looking different. That should be 2 times sine of 2x. Had too many 2's up there. Okay, so that's 2 times sine of 2 times x plus h. You just replace the x with x plus h, minus your f of x, which is 2 times sine of 2x. Okay. So your delta y is just your change in y. Where your dy is your differential of y. It's still just your change in y, but in a different form. Okay, so we know that dy is f prime of x dx. So first we have to find our dy dx. Which you know is equal to 2 times the derivative of sine of 2x. We just factor the 2 out to the front. So now we know, since this isn't just sine of x by itself, we have to use the chain rule for trig functions. Which means your dy dx is equal to 2. And that derivative, we know the derivative of sine is cosine. So that's cosine of 2x times the derivative of what's inside. Remember, the sine of g of x is equal to cosine of g of x times g prime of x. That's it. Okay, so we know the derivative of 2x is just 2. Move that up a little bit. So 2 times cosine of 2x times 2. So we can go ahead and just multiply these two together. So dy dx, move that up a little bit, is equal to 4 times cosine of 2x. Which means your dy is just equal to 4 times cosine of 2x. dx. All right, any questions on that one? All right. Okay, so let's say, for example, if we want to find your dy and evaluate when x is equal to 3 and your dx is equal to negative 0.4 for the function y is equal to 3x to the third power plus 5x squared. Okay, so remember your dy is just f prime of x dx. So your derivative of y with respect to x is just 3 times the derivative of x to the third power. So 3 times 3x squared plus 5 times the derivative of x squared, which is 2x. So your dy dx is just 9x squared plus 10x, which means your dy is 9x squared plus 10x dx. Okay. So we want to know that when x is equal to 3 and your dx is equal to negative 0.4, and your dy is equal to negative 9 times 3 squared plus 10 times 3. And your dx, we're going to replace that with negative 0.4. Okay, so now our dy is equal to everything in here comes up to 111. So we have 111 times negative 0.4. Oh, hold on. Nope. Yep, I think I was going the wrong way. Yep, and I do have it written down here. I was trying to do it in my head. Okay, so we have 81. Yep. 51 times negative 0.4. Let me double check my answer before I put that down.
Negative.
Yep, 20.4. Okay, so your dy is equal to negative times negative is positive, so 20.4.
Should the 9 be negative? Because it was positive earlier in the equation.
Why did I put negative? I'm like, okay, I knew it was 111. That's goodness. I need a nap. Yep, so that should be positive. So it was 111. I'm like, okay, I knew it was 111. I knew I didn't mess up that badly. But let me double check that just to be on the safe side. 81 and 30. Yep, now it was 111. That's why it was 1. Okay. I think I was thinking about that negative there and just for some odd reason put it a little too early. So that should be 44.4 if I'm not mistaken. Let me double check. Yep, 44.4. Negative. I have no clue why I put that negative 9 there. All right, so any questions on that one? Okay. Okay, anyone still writing? Okay. Oops. So let's say if we wanted to find dA, which is the estimated change in the surface area. If the sides of a cube changes from 9 to 9.2. Okay. So we want to find our dA, so a change in the surface area, which means we have to find the surface area. Okay. So the surface area of a cube is just the length times width of one side, but since a cube, all the sides are the same surface area, it's just the length times width times 6. Okay, so we have the area is equal to, and if we have our cube, kind of draw that out. And we'll just shade in the front. Okay, so the area of this side, we'll say that side of length S and this side of length S. So the length times width is S times S, or S squared. So if we add that area with the front, the back, the left, right, top, and bottom, that's just that same length times width times 6. Okay, so we know that the area is equal to 6 times s squared, which means the rate of change of the area with respect to the sides is equal to, bring down the 2, 6 times 2 is 12, so we have 12s. Well, if we put that in differential form, dA is equal to 12 times s ds. Okay, so we know that if the side changes from 9 to 9.2, then your ds is just equal to 9.2 minus 9, which is just your change in s, which is equal to 0.2. Now, if it decreased from 9.2 to 9, then it would have been negative ds. But since it's increasing, it's 0.2. And your initial, I won't put starting side, let's say initial side length. Your S is just equal to 9. So your dA is equal to 12 times S, which is 9, times your ds, which is 0.2. dA is equal to 21.6. So all this tells us is that the estimated surface area increased by 21.6. When the sides change from 9 to 9.2. It's kind of what that gave us. All right, any questions on that one? Okay, so let's look at some linear approximation examples. Okay, so let's say if we wanted to estimate, say, the cube root of 26.9 of f of x is equal to the cube root of x about the value of x is equal to 27 using linear approximation. Okay, so we know that our linear approximation is equal to f of c minus f prime of c times x minus c. When x is equal to c. Okay. Well, in this case, we know that c is equal to 27. That means your linear approximation is equal to f of 27 minus f prime of 27 times x minus 27. Okay, so let's find our f of 27. Well, we know f of x is equal to the cube root of x, so f of 27 is just the cube root of 27. Which is 3. Okay, so that's one part of it. Now, we want to find our f prime of 27. We rewrite our f of x to equal x to the 1/3 power. Makes that a little bit easier. Which means our f prime of x is 1/3 times x to the power of 1/3 minus 1, which is negative 2/3. Okay, now that one we can rewrite it to make it a little easier to calculate. So we can just say 1/3. And x to the negative 2/3, we can make it positive by moving it into the denominator. So x to the positive 2/3. And I'll draw a little side note here. So that x to the 2/3 power, we can rewrite that as x squared to the 1/3 power, because we're just multiplying those exponents. Or we can just say the cube root of x squared. Okay, so that means that our f prime of x is equal to 1 divided by 3 times the cube root of x squared. So if we want to find f prime of 27, that's just equal to 1 divided by 3 times the cube root of 27 squared. Give that a little more room. The root of 27 squared. There we go. Okay. But if you remember, we can kind of simplify this because the cube root of 27 is equal to 3. So we can write this as 1 divided by the cube root of 27 times the cube root of 27 squared. Okay. So we have the cube root of 27 times cube root of 27 times cube root of 27. That's just 1 divided by the cube root of 27 to the third power. So now we know the index and the exponent cancel each other out. So that means our f prime of 27 is just equal to 1 over 27. That means our linear approximation formula, if we go ahead and plug everything in, is L of x is equal to f of 27, which is 3, that's why I have negatives on the brain for some odd reason. That should be plus. I've just been writing negatives for absolutely no reason today. I have no clue why. Plus f prime of 27, which we figured out is 1 over 27, times x minus 27. Okay. But we want to estimate the cube root of 26.9. So the linear approximation of 26.9 is approximately equal to 3 plus 1 over 27. Instead of x, we can have 26.9 minus 27.
Is that supposed to be the cube root of 27 or 26.9?
Which, oh, nope, just 26.9. Yep, because the only thing you're changing is the x.
Okay.
Okay, so if you plug that into your calculator, you should get approximately 2.9963. All right, any questions on that one? All right, I'll leave it up for a few more seconds so everybody finish up. All right. Okay, so let's say, for example, if we want to use linear approximation of f of x is equal to sine of x at x is equal to pi to approximate sine of 183 degrees. And we want the exact answer and decimal to 4 places. Okay. So again, we know that our linear approximation formula is f of c plus f prime of c times x minus c. Okay. So we know in this case, x is equal to c means that in this case, x is equal, well not x, c is equal to pi, so probably a little clearer. So that means that L of x is equal to f of pi plus f prime of pi times x minus pi. Okay, so first let's find our f of pi. Okay, well, we know that f of x is equal to sine of x, which means that f of pi is equal to sine of pi. And sine of pi is just 0. I'll write it underneath there. F of pi is just equal to 0. So we can kind of save that one. Okay. Now we have to find f prime of pi. So f prime of x is equal to the derivative of sine, which is cosine. Which means that f prime of pi is just cosine of pi. And cosine of pi is -1. So f prime of pi is just equal to -1. Again, we kind of highlight that one. So our linear approximation formula, if L of x is equal to f of pi, which is 0, plus f prime of pi, which is -1. You could have put -1, but we'll go ahead and put -1, times x minus pi. Or if you want to just simplify it, you can just say L of x is equal to negative x minus pi. Okay, so we have our linear approximation formula for this question. Okay, so we want to approximate 183 degrees. The only problem is x minus pi show that it's in radian form. So we have to convert 183 degrees to radians, or in terms of pi. Or we could change this to 180 degrees, but if they want the exact answer, we have to leave it in terms of pi. Okay, so we know that if we have 183 degrees, to convert from degrees to radians, we just have to multiply it by pi over 180. So that's 183 degrees. I'll put degrees over 1 times pi radians divided by 180 degrees, where the units of measure cancel each other out. So we have 183 times pi radians divided by 180. And actually, that can be simplified to 61 over 60 pi. So if we want to find the linear approximation, I'll just go ahead and plug it in instead of writing the formula again. We got the formula already right there, so no need to rewrite it. So we'll just make that our 183 degrees. That's the same as saying the linear approximation of 61 over 60 pi. And that's going to equal negative 61 over 60 pi minus pi. Okay. Well, we can't add or subtract until we have like denominators. So we can rewrite that as negative 61 over 60 pi minus 60 over 60 pi, which is basically 1 times pi, which is still pi. Okay, so 61 minus 60 is just 1, so that's negative 1 pi, or just pi, over 60, which we can rewrite. You can leave it like that, or you can rewrite it as negative pi over 60. Okay, so this is our exact answer. And if you plug that into your calculator, you get approximately negative 0.0524. Rounded to 4 decimal places. All right, any questions on that one? All right. All right, anyone still writing? Okay. All right, so let's say, for example, let's say, suppose the side length of a cube is measured to be 7 centimeters. with an accuracy of 0.09 centimeters. Okay. So we want to use differentials. To estimate the error in the computed volume of the cube. Okay, so we know that our dy is just f prime of x dx. Okay, so what if we let S represent the side of a cube? Make that a little clearer. We have the side of a cube's length. Okay. That means the volume of the cube, which is the length times the width times the height, is just S times S times S. So it's S to the third power. Or you can just say V is equal to S to the third power. Okay. So the rate of change of the volume with respect to X is equal to with respect to S, so used to saying X, is equal to 3S squared. And if we wanted to put that in differential form, change in the volume is equal to 3S squared ds. Okay. So we know that the side length is 7 centimeters. Okay. And we know that the accuracy is 0.09 centimeters. So that means your dV is somewhere between 3 times 7 squared times 0.09 and 3 times 7 squared, should have given that more room, times negative 0.09. I'll write the negative 0.09 first. negative 0.09 times 3 times 7 squared. Okay, so that becomes, if you plug that into your calculator, you get negative 13.23 and 13.23. So the error is within plus or minus 13.23. All right, any questions on that one? All right. Yeah, we should be able to finish this last example. All right, anyone still writing? Okay. Okay, so let's say, for example, if we wanted to find the linear approximation. Uh-oh, running out of pencil lead. There we go. Find the linear approximation of f of x is equal to negative 7x minus 3 divided by 3x plus 1 at x equals negative 1, and use it to approximate f of negative 0.8. Okay. I was originally supposed to do this one second to last and the one I just did last, but I wanted to make sure that the accuracy one was covered and we had enough time. Okay. So we know our linear approximation is equal to f of c plus f prime of c times x minus c. So at x equals negative 1, means our linear approximation is equal to f of negative 1 plus f prime of negative 1 times x minus negative 1, which is just x plus 1. Okay, once again, we just go right down the line. F of negative 1, we just plug in our negative 1. So negative 7 times negative 1 minus 3 all over 3x, not 3x, 3 times negative 1 plus 1. Okay, so negative 7 times negative 1 is positive 7. 7 minus 3 is 4. we have -3 plus 1, which is -2. So it's equal to -2. So f of -1 is equal to -2. And we'll highlight that since we're going to have to come back to it. Okay. Now with this one, the f prime is the one that's going to give you the trouble because you're finding the derivative of a quotient. So we know that our f prime of x, we're going to have to use the quotient rule. So we have the denominator, which is 3x plus 1, times the derivative of the numerator, -7x minus 3, minus the numerator, -7x minus 3, times the derivative of the denominator. So the derivative of 3x plus 1 all over your denominator squared. So 3x plus 1 squared. Move that up a little bit. There we go. So that means our f prime of x is equal to 3x plus 1 times the derivative of -7x minus 3. That derivative is just -7. Minus, we have our -7x minus 3 times the derivative of 3x plus 1, which is just 3. That's all over 3x plus 1 squared. Okay, so we can go ahead and simplify this. We can distribute that -7 and distribute that 3, and still remember we have to distribute that negative. Okay, so our f prime of x, we distribute that -7. -7 times 3x is -21x minus 7. And if we distribute this 3, that gives us -21x. But if we distribute this negative, that makes it positive. So plus 21x. So if we distribute this 3, that gives us -9. But as soon as we distribute this, that gives us positive 9. So plus 9. Divided by 3x plus 1 squared. So we can simplify this a little bit more, only because the positive and -21x cancel each other out and equal 0. So we combine our constants. We have -7 plus 9, which is 2. So that simplifies to 2 over 3x plus 1 squared for our f prime of x. Okay, so if we wanted to find f prime of -1, that's equal to 2 divided by 3 times -1 plus 1. So 3 times -1 plus 1 squared. Okay, so 3 times -1 is just -3. -3 plus 1 is -2. -2 squared is just 4. So we know f prime of -1 is equal to 2 over 4, which simplifies to 1/2. So that one was a little bit lengthier than the others. So we can go ahead now, let me separate this a little bit, and plug that into our linear approximation formula. So plug it in, that gives us L of x is equal to f of -1, which we know is -2. Give that a little more space between the equal sign. There we go. Plus f prime of -1, which is 1/2, times x minus -1 or x plus 1. Okay, so this again would just be if they ask for the linear approximation formula at x equal -1, this would be it. But then when they throw in approximate a different value, that's when you plug it in. At x equals -1. So to approximate f of -0.8, we just have the linear approximation of -0.8 approximately equal to -2 plus 1/2 times -0.8 plus 1. Okay. So you can plug that into your calculator, or this one, you can probably do it by hand. So -2 plus 1/2 times -0.8 plus 1 is 0.2. And 0.2 converts to 1/5. Okay, so -2 over, let's say 1/10. I'll just go ahead and calculate it over here. Okay, so that -2, we can make that -20/10. So that -20/10 plus 1/10 is approximately -19/10. Bring that up a little bit. Okay, so that is our exact linear approximation. All right. Any questions on that one? Oh, okay. Okay. So remember, the exam module is open, along with the review and all of that good stuff. All right. So if you have any questions, of course, hang back, ask away. If not, I will see you tomorrow.
The exam module for part 1, and it said it opens on August 8th. It didn't let me take it. It's kind of weird. I don't know if you can look into it.
Yeah. Let me
Yeah. But like, it's so weird.
I'm like, August 8th.
Yeah. But let me know.
All right, I can look at that right now for you. Yeah, it does say August 8th. I don't know why. Sometimes it does that. It'll plug in its own. Yeah, you'll change it. It plugs in its own dates. I'll correct that. August 8th. No problem. Thank you for letting me know.
I think I'm in Canvas now, so I should be able to access everything.
Oh, okay. Yep. Let
So-
me check in 1 second.
Yeah.
Give me 1 second just to. Oops. Make sure everything here. Okay. Here we go. Yep. Okay. Now, guys, have to double check later and make
Okay.
sure that it stays.
Okay,
Yeah.
and then as for deadlines,
Mhm.
is there a time I should finish or get caught up by?
Let me see. Make sure you're actually listed. Yep, you're here. All
Okay.
right. So what I can do is. Uh-oh. Let's see. What's today? The 3rd. Let's see. Look at the calendar. Okay. Figure what I can do is. Oh, let me